Hello, everyone. Let's begin today's recitation. Hi, I'm Samruddhi, and we have Moyad with us.
Hey
Um,
guys.
yeah. So today's recitation is on summarizing the hyperparameter tuning methods, which you have been seeing throughout your homework part 2, and it was also introduced in recitation 2. And apart from that, we'll be introducing many more normalization techniques, ensemble methods, and how you can make the most out of your study groups. From recitation 2, we learned that hyperparameter tuning is required for improving your accuracy. It also helps in converging your model faster if you choose right parameters. It is also important for understanding what hyperparameters are and how we tune it, because we have resource constraint and we cannot randomly put it on grid search, which will come up to later. And most importantly, it's required for climbing higher on the leaderboard, like you all might be knowing by now. So, we saw various hyperparameters like learning rate scheduler, optimizer, dropouts, etc. in previous recitation. And we also learned what all values are there to be tuned and how can you tune these hyperparameters. There are some other techniques which was introduced by Professor during last Wednesday's lecture, as well as in recitation 2. Those are like early stopping, gradient clipping, augmentation, using mixed precision training, etc. As far as strategies for tuning hyperparameters is concerned, we have grouped them in these two parts. One is kind of babysitting your model, which is like you start with one base model and then keep on tuning your hyperparameters for that particular model. The other one is a caviar approach, where you have like lots of models in parallel and you have various hyperparameters for each model and then train them parallelly to see the performance. So uh, as this diagram shows, I think most of you would agree that there are different types of headaches, but tuning hyperparameter is a real one. So why is compute requirement necessary and why do we take it into consideration? That's because majorly for us as students, we do not have access to a lot of computing resources. And so choosing the right strategy to tune hyperparameter is kind of directly related to what computational resources you have access to. So as we can guess that babysitting approach will definitely require less compute than the caviar approach. Um, but it also results in spending a lot more time because you do not have your models running in parallel to identify which one works better, but you need to sit and tune each and every parameter sequentially. So other suggested trade-off by us would be to train some baseline models in different configuration first, like have a subset of the parameters, and then you can shortlist some of the promising models out of it and then further tune those. If at all you are lucky and you have like unlimited compute, there are many more tools such as grid search, um, wherein you have basically a range of values which each hyperparameter would take, and you run your model on each and every possible combination. Or you also have like Bayesian optimization techniques, and there are Python supported tools like Raytune for that. One of the most practical work around for this course, at least, would be dividing these hyperparameter searches amongst your study groups. And that would necessarily be equivalent to like running format models in parallel. So yeah. Oh, sorry. My Siri got triggered for some reason. Sorry about that. Yeah. Coming to the logging methods. So I think like we all of us in the beginning might think like why it's such a big deal and why are we uh, forcing you all to log. We have that weights and biases code in the starter notebook as well. But most of us who have been in CMU for long would agree that CMU likes to keep us busy and there are multiple things going on in parallel in everyone's mind. For those whose this is the first semester, ignore what I just said and enjoy your time as long as you can. Just kidding. So yeah, so we generally, because there are a lot of experiments going on for this course, and you also have other courses, you might be taking DL and other courses as well. So there are high chances that we mix up the hyperparameters and forget which model was performing very well. So it's always suggested to log your experiments properly. So yeah, as one of the famous American authors and filmmaker once said, if you do not know history, then you do not know anything. You are just like a leaf that doesn't know it's part of a tree. So it is, as I said, mandatory for all of you to log your experiments in a very organized way, because that would eventually help you. And it will also be a good habit to follow in general. Uh, Two suggested methods would be using Google Sheets or Excel and logging it manually. And another semi-automated fashion would be using weights and biases, which was again introduced in the Recitation 2. And by now, all of you might be familiar with it because you have been using it in part 2. This is kind of an example of how you can log your experiment using a Excel sheet where you have like one column dedicated for all your hyperparameters, and then you keep on like adding values to it and have some color coding to kind of make notes of what worked, what did not work, and so on. So yeah, just to summarize that sheet, you can include all the parameters and track them in the sheet. Color coding helps a lot to uh, makes it better visualizing it, and also makes it easier for understanding. And so one suggestion would be to start training simple models and then see what is working and then methodically change based on your result. Um, so this helps you to develop an intuition easily, since you're tracking your hyperparameters yourself. So rather than using weights and biases and letting it do its tracking back, and you have to like look at the sheet, understand what parameters you're using, and then analyze what is working, what needs to be changed. But of course, this is a lot of manual work, and that also takes in some time. Yeah. But as I said, because you are monitoring the sheet manually, you develop an understanding of what is working for you. So that builds up your inference from the past experience. So as it's mentioned here, hyperparameter tuning is one of the most important part of deep learning pipeline. And depending on the task at hand, and the data set you are using, hyperparameters need to be tuned very carefully. So, and of course, throughout the homework part twos, you will be getting a good idea of tuning hyperparameters. since that's what you would be doing after your early submission necessarily. And seeing the competitive nature from the leaderboard in for homework 1 part 2, I think all of you would take this seriously as well. So, but yeah, please note that hyperparameter is not an exact science, or there is no math behind it that if XYZ is my data set, then this is going to work for sure. Or if I'm training on speech, then this should be the best model. Such things do not uh, relate directly. And hence you might have been like seeing that we suggest various models, and then even in your study groups we have had students coming up in OH and saying that, oh, this is working for my study group but not for me. There are very fine details to it, and like even a value of some small parameter, like maybe a learning rate being different in the beginning, or your scheduler being different, your optimizer being different, might uh, change the way your training is going to proceed or converge. So having said that, after like going through a lot of experiments, you will have to work on empirical evidences to guide your choice, because even though it's not a science, but you will have to eventually develop some intuition on what works and what is not working. So this makes it crucial that you stay up to date with the recent research papers and you discuss all of these things with your study group. So deep learning also involves some kind of human learning component to it, which is this manual hyperparameter tuning. So you can operate a bit on the domain knowledge, sorry, you develop through your experiments. And also understand that please do not form opinions based on one or two failed experiments, or even the other way around. If one or two experiment is successful, it does not mean that even if you're changing like one particular parameter and that improves your accuracy, there might be some indirect relationship going on between other parameters, which is helping you. So yeah, and to understand this journey overall, like what is helping and what is not, it is very important that you change your parameters successively and not by huge factor, because if you change multiple hyperparameters at a time, you will not realize what actually helped in increasing the accuracy or decreasing for that matter. Yeah, just to reiterate, domain knowledge is important and could help you build models more efficiently. It is of utmost importance to understand the task you are training the model for, as well as the domain for that particular task. And if you do not have intuition in that domain or the model you're training, read more papers and work with study groups. It is very important for this course and in general whenever you're working with deep learning model. So giving an example using homework 1 part 2, because probably that would help you relate the most to. So what does domain intuition exactly means? It's, for example, since you're using phoneme classification for your homework 1, that's why we are suggesting you to use context. So that's kind of the domain knowledge which you develop eventually, and analyze like what is your training data, what is the model, will this model work best with these kind of augmentation. All these things are based on the domain intuition you develop. So start your work with several simple architectures, which is why we also have like early submission deadline where you at least build a simple architecture and get your pipeline up and ready, and then eventually start hyperparameter tuning and find the best combination possible and change your hyperparameter. That should be hyperparameter. Sorry about that. Change your hyperparameter settings to see if there is any improvement eventually. Here is an example of, again, the same sheet which you saw initially, but this specifically shows how to make small changes. For example, you started with this particular experiment 1 with context size 8, 2 hidden layers, activation as ReLU, and your architecture was pyramidal, and you did not use anything else and had Adam as your optimizer. So maybe after seeing the performance, you decide on like improving your context size first and see uh, how it was performing. Then maybe change your architecture to cylindrical and then keep other things same, and maybe like uh, so in the first experiment, you realized that 16 was working better. You fixed it to be 16, and then in the second one, experimented more with the architecture and optimizer, and so on. Gradually, keep on changing a couple of things as you move, as you experiment with other models. So that's about, yeah. Go on, Indranil. You can
Yeah, I
unmute
had a
yourself.
question on the previous
Yeah.
slide.
Yeah.
Yeah, I was just curious, like, maybe I missed it in the lectures, but like, what is the difference between the second experiment and the third experiment in terms of activation? So in the second experiment, we used ReLU, and in the third experiment, we used soft plus ReLU. I'm not exactly sure what the
No,
distinction is.
so they are like just it's not you're using soft plus redo. It's like probably trying with soft plus, keeping everything same from the second experiment, and then like changing your hidden layers that way. So is that your question?
Um,
So from
I'm not
ReLU, you go to using soft plus and probably the third experiment.
in all the hidden layers.
Yeah.
Okay, got it. Thanks.
Yeah. And it's also possible to have a combination of hidden layers, not necessarily you use like a combination of activations, not necessarily you use one activation throughout your model.
Okay, interesting. Got it.
Yeah. Is there any other question?
Yeah, I have a question. Can you hear me?
Yep.
Yeah, in one of the slides you mentioned that we should save our model, make checkpoints after every epoch. Um, Here, while doing experiments, when we save and when we make a checkpoint, we change either context or an architecture. It's gonna be a different model essentially. So will we still be? What's the point if we're gonna be changing the model gradually? We can still reuse it. I don't know if that makes sense.
Yes. I was losing you in between, but I think what you are asking is why do we need to save the model after every checkpoint? And if we make small changes like increase the context size in between, that would be another model altogether. And then
Yeah,
will it make sense to save it, right?
yeah, exactly. Yes.
Yeah. So the point behind like saving your model after every checkpoint is that uh, okay, you are like introducing redundancy in it, and like just using a lot of memory to save the models, but at the same time you have an option of going back if something does not work when you're tuning something else. Like maybe you change your context to 50 and then realize that, oh, maybe that this is too large and it's not giving me that good of an accuracy, and my model with 30 was better. So if you save it at each and every checkpoint, you have an option of like going back and forth between the models. You can have some conditions while saving, like probably you can check if your accuracy is increasing or not. And if it's increasing, then only save, because you want to have like the best model saved. So you can have conditional save. One other important advantage of saving your model is majorly when you're working with Google Colab, your session gets disconnected uh, once in a while. So at such times, you can resume your training from your previous checkpoint rather than like wasting up all the time you have used in training. Is that making sense?
Yeah, that makes sense. Thank you.
Yeah.
Hi, I have another question.
Mhm.
How many epochs would you say we would need to train for when we're doing this hyperparameter tuning? Because there are some hyperparameters, like say the scheduler, whose effects might not be seen in like just a few epochs. So each time, do you think we'd have to train for like 20 epochs? Because that would take like quite some time, right?
Yes, but as you have pointed it out yourself, like for some hyperparameters, you not even just the scheduler, but there are many more, like maybe even the dropout. Initially, when you add dropout, you would see that the model is not performing that well, but that's because you are adding some regularization to it, which forces it to generalize well and not overfit. So you won't get high like increase in accuracy immediately.
Yeah.
So in such cases, you will have to train it for some number of epochs, like to see the trend, unless and until you see that, oh, it's not working at all and my accuracy is decreasing all the time, or my model is overfitting with this, you can stop the training early. But apart from that, like in regular cases, you will have to give it some time and train for the standard number of epochs you have been training each for your each experiment.
Okay, thank you.
Yeah. So moving on to normalization techniques. So there are multiple normalization techniques, and again, this is one of the reason why uh, we were saying that you have to stay up to date and read papers, because every now and then there are like different techniques coming up and different papers are getting published. So yeah, all of you have seen what batch norm is. You all might have also been implementing it in your homework 1 part 2, and professor gave an amazing explanation about what batch norm is in this week's lecture. So apart from that, there are other normalization techniques like layer norm, weight norm, instance norm, group norm, batch instance norm, and switchable norm. I have also linked papers to all of these norms here. So once the slides are up on the website, you can have a look at it. Summarizing batch norm a bit, uh, you have seen what batch norm is, how it works, what are the equations for batch norm in the lecture this Wednesday. So in today's recitation, I wanted to point out the syntax for all these normalization techniques, and then you can definitely go back to the paper and understand in detail how it works. In batch norm, we normalize the input over the entire batch. This is to eliminate the internal covariate shift. So Torch has its implementation for batch norm 1D as well as batch norm 2D. The batch norm 1D is used when your input is in 2D or 3D dimension. Like, for example, the input you have in your current homework. For 4D input channels, you use batch norm 2D. One of the examples would be using batch norm with CNNs, which you will be seeing in your homework too. So in such cases, you might be needing batch norm 2D. In terms of implementation, it's quite straightforward. you generally use it in between linear and activation, in between like your normal layer and the activation layer. And you pass in the number of features, which should be same as the output of your previous affine layer. But layer norm came into picture to kind of work around some of the problems we face with batch norm, which is if the batch size is very small, whatever mean and variance we are calculating from that batch size might not be accurate, or say for example, you have some outliers in your batch size of 2. So that would swing your mean and variance a lot. So for such cases with smaller batch size, batch norm does not perform very well. And okay, one workaround for this would be, why not have a large batch size always? Why do we go for smaller batch sizes? But think of a situation where you have very high dimensional data. Like for example, with high resolution images, if you flatten it, it becomes really huge in size. And then for such cases, because of memory constraint, you cannot fit in a lot of inputs together. So you have to reduce the batch size to fit your input in the memory. So in such cases, batch norm performs poorly. One other disadvantage is maybe calculating running mean and average, variance might not be the best thing for sequential algorithms like RNNs, because in sequential algorithm, you depend on each and every input, and at that time, uh, normalizing it across batch is not a best option. Instead, we want to normalize each and every input individually, and that's where layer norm comes into picture. So in layer norm, you calculate the mean and variance for each item within your batch and then normalize using those parameters. Syntax is similar to batch norm. It's toss.nn layer norm, and then you pass in the normalized shape. So some other methods, like the first slide also mentioned, are weight norm, where you directly normalize your weights and not the inputs to the layers. In that case, you have to specify the layer for which you want to normalize the weight, and then pass the name of the parameter, like whether it's weights or bias, all of those things. Remember that layer norm, batch norm comes in the toss.nn module, but weight norm is inside utils. So you can always go back to the toss documentation to get the syntax. There's also something known as group norm, where it is kind of a combination between the layer norm and your batch norm. So you take a group of your batch, like club multiple inputs together and then normalize over it. Instance norm is basically normalizing individual channels or features for each input. So for instance norm as well, you have two options, 1D and 2D, and the meaning is same as you saw in batch norm. It depends on the dimensionality of your input. Here are some reference materials. The first link is a document on all of these norms, and it has like some explanation for it. The second one is your basic PyTorch documentation to get the syntax. Summarizing the story of norms, I think this helps in developing the intuition in much better way. So here, if you see for batch norm, we normalize it across n, which is like for your entire batch. For layer norm, we take one input and then normalize across the features or the channels for images. Instance norm is just one feature for one particular input, and group norm is subset of layer norm where you club multiple channels together and normalize over it. Any questions so far? So now that we are done with hyperparameter tuning and normalization techniques, Moyed will take it forward and explain ensemble methods.
Okay, so what we've been learning so far during our course is that when we create a neural network, the idea that we're trying to do is we want to make a hypothesis of the data, and that will help us to classify or get more information about it, and then make our predictions later down the line. So what Ensemble does is it will divide the data basically into a number of features, and then all these get learned by different classifiers or different models. So the idea here is that each different model will learn a subset of the features and will learn to classify those well. And then at the end, we will group them together in a way that will allow us to get better results than when you use one single model to learn all the different features of our data. So the first way that we do this is called bagging. Here, the idea is we use different models, but we feed the data to them in parallel, and we try to make each model learn a different subspace of the data, and then at the end we combine them, aggregate them, and to get our final decision. So the idea here is we want trying to decrease the variance of our models by letting each model learn a subset of the feature space. The other way that we can do this is that we will use boosting, which is an idea where we will sequentially get the output from each model to the new model, allowing each model to learn from the experience of the past model. So one problem that might arise from the bagging method, that if there is a couple of features that are strong in the data set, each model can learn these features, and then the performance will be not better than if you use only one model. So here we want the models to learn from previous models' mistake, and then we will aggregate the decisions from all of these models together. The first one will reduce the variance as we described, and then the boosting will decrease the bias for a specific set of features. One method or one algorithm that we can use that's an example of boosting is called XGBoost. So the idea of XGBoost is that we want the model to learn from the mistake of previous models. Each model should learn from the mistake of previous models. Sequentially, we will feed the output from our previous model into the input of the next model, and we will adjust the data accordingly to make sure that we learn different features or different decision boundaries. So if you've ever been in any Kaggle competition outside of the course, you would know that XGBoost is one of the most powerful models that people normally use to get on the top of the leaderboards. And yeah, so it's like a cheat code for many tasks. So the idea here is the first classifier will generate a decision boundary going from here to here. Then we use this output will increase the weight of the features that have been learned incorrectly. So this red plus sign has been learned incorrectly here, and those two blue minuses have also been classified incorrectly. This is the input for our next model. This next model is going to learn a different subspace or a different decision boundary here that will classify the bigger weights. And yeah, this one also includes some errors. Then we will increase also the weight of these errors, and then we can learn a final classifier so that at the end we will have a classifier that will classify all of our data points correctly. So one might run to use ensemble methods for this specific homework, which is fair game, but you have to remember that we only have 20 million parameters. You can't use the same model that you're using now 3 or 4 times and expect that you're going to have the same number of parameters. So you have to use, you have to be diligent about that. Use smaller models, try to combine them in different ways, try bagging, try boosting. Maybe instead of using all a specific algorithm, you can just decide on the final one, getting a novel idea or something like that. And yeah, just make sure that you're within the 20 million parameter limit that we have. So the last thing that we want to discuss is study groups. So the study group distribution have been posted already. There are some groups that are still being edited, but for the most part, you either got communication from your mentor or you will get in the next 2 days. So why study groups? So they allow you to get more from the course. So when you're learning alone, something as deep, no pun intended, as deep learning, you would want to get information or input from other people. So this will allow you to get more information from people, get more viewpoints. Some people might have different experiences than you. Some people might have read more paper than you, or even you might have read different stuff. You have different experiences. So getting all this together in one place will allow the 3 or 4 of you to get more knowledge than what you've gotten on your own. This will also allow you to move towards a caviar hyperparameter tuning method. So the issue with caviar method that we mentioned is compute. We don't have unlimited compute. For this first homework, most of us are using, or all of us are using Colab or Colab Pro. This is still not enough compute for you to do whatever you want. So if you, for the later homeworks, you're going to submit, if you worked alone, you're going to submit like a $20 model. This will allow you to get more out of it, to get an $80 or $100 model, which will definitely have more information, and you will perform better in the homeworks. And that leads to the final point: is this will allow you to get high cutoffs. So this is one of the reasons that we were like a lot of the people that took the course have seen differences between them doing like work alone on the first homework and then them shifting to working together in the second homework. Which the second homework is going to ramp up the difficulty and the amount of tuning that you need to do. So for that one, you have to start using your study group in an efficient manner. So how do you get the most out of the study groups? You just start contacting each other. The sheet is already posted. Go find your study group, start contacting each other, create a way of communication. You should contact your mentors if they haven't contacted you, or reply to their contacts. You should join the Slack channels that you've been sent invitations to, or you will be sent invitations. And you should start creating relationships. I mean, like we've been saying a lot about relationships in this recitation, and they are really the way to get high cutoffs in these homeworks. And you need to meet regularly. You need to meet to discuss the lecture material. You need different meetings to also work on the quizzes, and you need to also start working on the homeworks together. And you also, for later on, you're going to start working in the group. So you need to make sure that you dedicate enough time for each one of these things and to be able to get the most out of it. So what a good ablation sheet looks like, normally, like we said, you're going to start with a simple hypothesis, then someone else is going to do a variation of it. And maybe for this one, we use the baseline model, which was this. The second one replaced the ReLU with GeLU. The third one added less batch norm, meaning that you change from using each layer to each other layer. We see here that maybe they have found like better performance. So then you use this baseline and then you add to it, and then you add to it. You might do this, each person will do it individually, but a better way to do it is define a sweep. So starting from here, let's go, and one person might run a sweep through different context sizes, different learning, different dropout, different learning schedulers, different activations, different optimizers, and then they will report like the best that they got from here. The question was asked earlier, but later during the semester, you're gonna figure out like after how many epochs you should expect the models to be different. So maybe for this first homework, after 5 epochs, you might get a decision if this model is performing well or not. Later on, it's going to be also like you're going to find the threshold where your model is, you're going to be sure that okay, this model is going to be good, this model is going to be bad, and then you can start doing this. You will do this at the start, either with the full data set and like a couple of epochs, or using just a part of the data set and then running for longer and longer. This won't be the same case because later on, when you get different data sets and you want to do more complex tasks, you're going to have to train on the full data set. But either way, define a sweep, train that sweep, get initial ideas about which hyperparameters might be better than others, and then train longer on them. So this is how we do it. So normally you would like to report the training loss, the validation loss and accuracy, and then the test accuracy. You might include other things like normalization, regularization, and you want to report like in writing what worked and what didn't work. So in this manner, you can reuse this. You will reuse the sheet in some manner because there are some similarities between the homeworks in some parts. So you would want to know like what kind of work in speech data versus what kind of work on image classification tasks. And yeah, so as you've seen, there are too many choices to make for hyperparameter tuning. So using your study group, contacting the mentors, contacting each other, meeting regularly is one of the ways that you can, jump through the hurdle of homework 1 part 2 or homework part 2s and get to better grades. So any questions?
I just want to add one thing here. Mohit, can you go back to the previous slide? Just for reference. Yeah, so we are saying that, okay, you develop some kind of intuition by seeing what performs better and then gradually build on it, or maybe take like some of you work on like 25% of data, some of you are working on full data as mentioned here. But again, all of this is kind of a trade-off because we do not have sufficient compute. So this might be confusing for some of you guys, where we also say that, oh, it's not an actual science that you say this is working, this is not working, but at the same time we are saying get some intuition. So that's only because like the best optimal way to do this is to uh, have like grid search over all the data set you have possibly, and then search for each and every parameter having a sweep. But that is not always possible because of the compute available to us and because of the time. So for that, all these things are kind of a trade-off, like, or you can judge your performance on some part of your data set. But again, none of these like always guarantee you, as Mohad also mentioned, like if something is performing good on a subset of data, it might not work well for the entire, or the other way around. Your model might be good enough, but the data is less, or actually not the proper distributed sample of your entire data set. So in those cases, translation might not be that straightforward.
Yeah, and all of this is just a way for us to take some of the like you might feel sometimes that you're just trying out random things, but this is a way for you to be able to make sure that you're actually okay. I want to know what this means, what this means, what this means, and not just to get high cutoffs. You want to learn like what this does, what does the context do in this term. You want to do okay, should I be using like this type of normalization here, this type of normalization here, and through doing that, you will get more understanding of what they do actually, and yeah, that's like really important. Okay.
Yeah. So yeah, go on, Anthony.
Yeah, I was wondering, would you be able to share some intuition on like how you guys selected the number of neurons in the hidden layer? So in the examples that you've given, you've selected like 512, 512, and 256. Like, is there any is there any intuition among for selecting number of neurons in the hidden layer, or is it usually trial and error?
I mean, this is just a trivial example, so this isn't like a real application, this is what it looks like, because we don't want to give you the answers to it. But normally you would want to understand like, how do I increase? Okay, so you see here that we started with a baseline model that, okay, this is a smaller model, just take the data and expand it a bit and then go through, then decrease it. So maybe this didn't perform well. Let's try and like expand a bit. Let's try and find more features. Let's try and expand, like, our representation of the data, then try that again. So some of it is understanding the problem and what do you want like your architecture to do, and some of it is like, yeah, normally people just try a bigger model, more layers, wider network, and but the thing is, the issue here with this course and these homeworks is that you can't always do that. This won't always get you the best results. Like, there's a trade-off that you have to do, and then again, like, you have compute issues. You can't for this homework, you can't train a 25 million or 30 million parameter model. That will get you through the high cutoff, yes, but like, we need you to think about other things about it. Yeah.
Okay, thank you.
Are there any other questions? If not, then I think this was today's recitation. And do you want to add anything more to it?
Yeah, just join the Slack channels when they're sent to you, please, and make sure that you talk with your TAs. Yeah, we're here to help you.